Hello, my friend. I'm glad you're here tonight. Maybe the day has been long, or maybe you just want to drift into sleep with a thought softer than silence. Let your shoulders ease, your breath settle into a slow rhythm, and let the world outside grow dim. You are safe here. Tonight, we'll wander into a strange and beautiful idea: what might happen if a white hole, a fountain of light and energy, ever met its dark twin, a black hole that swallows everything it touches. It's a cosmic meeting of opposites, creation and destruction dancing at the edge of space and time. You don't need to understand it all. Just listen. Let the images float like stars behind closed eyes. And if these quiet stories bring you peace, you can gently tap like or subscribe, so the next time you need rest, you'll find your way back with ease. Now, take a slow breath. Let's begin. Imagine you and I, beneath a dark sky, tracing questions too large for daylight. Somewhere far away, beyond the reach of any telescope, two impossible beings might be waiting to meet. Scientists still wonder if one of them, the white hole, exists at all. It's said to be the opposite of a black hole, a fountain instead of a drain, where nothing can enter and everything is pushed out. And yet, the thought of such a creature crossing paths with a black hole makes even the calmest minds stir. What happens when creation and consumption meet in the same breath of space? A black hole, after all, is gravity made pure. Picture something so heavy that not even light can slip away from it. Around its heart lies a border called the event horizon, an invisible shoreline. Cross it, and there's no coming back. Yet at that boundary, nothing feels different. No warning, no shimmer, no pull to mark the crossing. It's one of nature's softest tricks, the point of no return hidden in stillness. Einstein's great equations first whispered the possibility of such monsters, a mass so compact it folds space itself. Later, Stephen Hawking added another quiet truth: black holes are not completely silent. They hum faintly with something called Hawking radiation, like the coldest ember glowing at the bottom of the universe. The warmth they give off is smaller than small, too faint for any machine to touch. But the idea of these dark wells is older than Einstein. Long before relativity, two thinkers, Jean Michel in England and Pierre-Simon Laplace in France, imagined stars so dense that light could never leave them. In 1784, Michel even guessed how such invisible stars might betray themselves by the tug they cast on the ones we can see. For a time, the idea flickered, then faded, as new theories of light rose and the mystery seemed to dissolve. And then, in the early 1900s, the thought returned stronger, stranger, and true. Einstein finished his general theory of relativity, and not long after, Carl Schwarzschild found a precise shape hidden within its math. He drew the first clean outline of a black hole, the sphere beyond which space caves inward. Others refined it, gave it form and name, until the impossible became part of our sky. Somewhere in that slow unfolding of ideas, the universe began to tell us that darkness can have structure and silence can speak. There's a quiet rhythm in the life of a star, a long, glowing breath between its birth and its final fall. Some die gently, fading into white dwarfs. Others collapse in silence so deep that even light cannot return. In the early 1930 seconds, a young Indian physicist named Subrahmanyan Chandrasekhar sat on a ship from India to England, doing calculations that would change how we understand that final breath. He found that if a star grew too heavy, more than about 1.5 times the mass of our sun, it could not hold itself up against gravity. Beyond that point, there was no balance, no rest. collapse would continue forever. His peers, even the great Arthur Eddington, doubted him. The idea sounded cruel, even absurd, but time, as it often does, sided with the quiet truth. Stars that reach that limit fall inward, crushed by their own weight. Some stop as neutron stars, dense orbs no larger than a city but heavier than the Sunday. Others continue the descent, slipping past the boundary where nothing returns. That is where black holes are born. By the middle of the 20th century, scientists began to see black holes not as mathematical tricks, but as real creatures of the universe. They found one of the first in the constellation Cygnus, a faint point of X-rays flickering across space. The star that circled it seemed to be dancing with a partner it could not see. The invisible companion, massive and silent, was feeding drawing gas from its twin, spinning it into a bright, hot halo before swallowing it whole. They called it Cygnus X1. The name sounds cold, but what it revealed was something alive, a window into gravity's deepest hunger. Every black hole begins with an ending. When a massive star burns the last of its fuel, there is nothing left to push against its own pull. The core collapses inward, atoms crushed, light bending around itself. The star's outer layers explode in one final blaze, a supernova, while its heart becomes infinitely dense. The more it feeds, the more powerful it grows. Some become monsters millions of times heavier than the sun, sitting in the hearts of galaxies. Our own Milky Way has one, a quiet giant called Sagittarius A, asterisk 4 million suns compressed into a point that could fit inside Mercury's orbit. We can't see it directly, but we can feel its presence. Gas and dust spiral toward it, heating to unimaginable temperatures, glowing in radio and X-ray light. Sometimes, this feeding lights up entire galaxies, quasars. They're called shining brighter than everything else combined. It's strange, isn't it? Something that swallows light can also be the reason the universe shines so fiercely. The deeper scientists looked, the more patterns they found. The limits Chandrasekhar had uncovered turned out not to be alone. In 1939, Robert Oppenheimer and George Volkoff showed that even neutron stars, those dense remnants, had their own breaking point. To push them too far, and they too would collapse into black holes. Later, that limit was refined, using the subtle forces between particles, landing somewhere near twice the mass of the Sunday. In 2017, when two neutron stars collided, their light and gravity rippling across the cosmos, it gave us the most beautiful confirmation yet. Out of that collision, a black hole was born, and the universe itself rang with its birth cry. That same year, 1939, Einstein tried to prove that such collapse could never truly happen. He thought nature would forbid it, that the equations of his own theory would somehow resist the abyss. But only months later, Oppenheimer and his student Hartland Snyder quietly showed the opposite. Using Einstein's own mathematics, they demonstrated that the collapse was real, inevitable, unstoppable. They imagined what it might look like. To an observer far away, the collapsing star would appear to slow down, its surface freezing in time, at the edge we now call the event horizon. They called these frozen stars, unaware that future generations would give them a darker name. Decades passed, and understanding deepened. In 1958, David Finkelstein gave language to that mysterious boundary, the event horizon, a one-way door through which nothing escapes. Around the same time, Martin Kruskal found a new way to draw the map of space-time, showing that from inside, the fall continues smoothly, endlessly. Together, their insights lifted black holes from theory into geometry, from numbers into shape. By the 1960 seconds, black holes had become the beating heart of physics. Roy Kerr discovered the form of a spinning black hole, not just falling inward, but swirling, dragging space itself in its wake. Soon after, others extended his work to describe black holes that carried electric charge. Out of these discoveries came an elegant truth called the no-hair theorem. No matter how a black hole forms, it forgets all details of its birth. Only three things remain: its mass, its spin, and its charge. Everything else is erased. That simplicity is haunting. It means that two stars, different in every way, could die into the same kind of silence. A reminder, perhaps, that the universe loves symmetry more than story. Then came the proofs that ended all doubt. Roger Penrose and Stephen Hawking showed that singularities, points where space and time truly end, are not curiosities of perfect math, but real outcomes of collapse. Their work pulled the idea of black holes out of the margins and into the center of physics. Penrose would one day win the Nobel Prize for it. Hawking's mind, meanwhile, would carry the idea further to the edge of paradox. He proposed that black holes, while dark, are not eternal. Tiny fluctuations in the vacuum around them can create pairs of particles, one falling in, the other escaping a faint glow, called Hawking radiation. Over trillions of years, this glow could cause a black hole to slowly evaporate, fading like the last coal in a dying fire. Astronomers, too, began to see with new eyes. In 1967, Jocelyn Bell Burnell noticed strange pulses in radio data regular, like a heartbeat from the stars. These were pulsars, the spinning remains of neutron stars. They confirmed that such dense remnants truly existed. Soon after, the discovery of Cygnus X, one proved black holes did, too. And then came a century's worth of silence broken by sound. In 2015, two black holes collided 1 billion light-years away. Their crash sent ripples through space-time itself, gravitational waves that reached us, faint but unmistakable. When LIGO heard them, the Earth literally trembled with their echo. It was the first time we didn't just infer a black hole's presence, we heard it sing. A few years later, in 2019, the Event Horizon Telescope gave us something we never thought possible: a photograph of the unseeable. A golden ring of light encircling darkness, the shadow of a black hole in the galaxy, M87, 55 million light-years away. A human eye, stitched from telescopes around the world, peering into infinity. Since then, the discoveries have continued. The Gaia mission revealed nearby stars orbiting invisible companions, hidden black holes not far from our own Sunday. There may be hundreds of millions of them in our galaxy alone, quiet and unseen, moving through the dark like slow, invisible tides. And even the words we use to describe them have a story. The phrase black hole wasn't coined by a single hand. It was whispered, shared, passed along from early writers comparing them to the Black Hole of Calcutta, to journalists describing black holes in space. Then, in 1967, the physicist John Wheeler spoke it aloud at a lecture, and the name stuck. The words carried weight, mystery, finality, and so the universe gained its simplest metaphor: a whole, not in matter, but in meaning itself. Now we speak of them as if we've always known, as if humanity didn't spend centuries chasing shadows before realizing they were real. Yet, in a way, the mystery hasn't lessened. The more we learn, the quieter the universe seems to grow, as though knowledge itself bends toward stillness. Somewhere out there, a black hole drifts unseen, its gravity shaping light, its silence shaping thought, the cosmos keeping one more secret in the dark. Picture a still lake under moonlight. You drop a thought into it, and the ripples move outward, gentle and sure. Gravity is like that curving space and time, so that paths bend and fall. Now imagine a place where the curve grows so steep that every ripple tips inward, where even light, swift as it is, finds no path that climbs back out. That is a black hole in the quietest phrasing, a region where escape would require faster than light speed, which nature does not allow. In the language of Einstein, it's a mass pressed inside a boundary we call the Schwarzschild radius, a mathematical shoreline beyond which all trails lead down. From far away, this shoreline hides itself. The gravity of a calm, non-spinning black hole looks exactly like the gravity of any spherical object of the same mass. A planet, a star, a perfectly even sphere. Swap them at a distance, and you wouldn't notice the difference. The drama gathers only near the edge, at the event horizon, a surface with manners like velvet. No flash, no sting, no signpost, just a one-way door. Cross it, and every possible future points inward. What survives of identity in such a place? Physics answers with a stark simplicity called the no-hair idea. After all the storms have faded and the black hole settles, only 3 traits remain for the outside world to measure: mass, how much; spin, how fast it twirls; and electric charge, how it leans in the balance of positive and negative. Everything else, the shape of what fell in, the pattern of fields, the messy particulars washes away. If 2 black holes match in these 3 numbers, they are indistinguishable to the universe beyond their horizons, elegant and a little eerie. Those 3 traits are not abstract. Mass reveals itself in how orbits curve, a kind of gravitational Gauss's law writ in the dance of distant stars. Spin shows up as frame dragging, where the rotating hole tugs on space-time itself, twisting the local flow so gently at first, then fiercely near the rim. Charge, if it exists, pushes and pulls like any charged object would, though nature likely keeps most astrophysical black holes nearly neutral, the way stars are. Spin, by contrast, is hard to avoid. Collapsing matter carries its rotation inward, and what was once a lazy twirl can become a hurricane. Much of black hole physics can be told through a story about surfaces. The event horizon acts like a thin, resilient skin. In one useful picture, the membrane paradigm. To the mathematics outside, this skin has electrical resistance and viscosity, as if currents can flow and heat can dissipate along it, smearing the memory of whatever plunged through. This picture is not literal. Nothing material sits on the horizon, but it's a brilliant bookkeeping trick that lets physicists translate the complex geometry into more familiar language. In that language, information about the fine details of what falls in seems to disappear for any outside observer. That suggestion leads to one of the strangest puzzles in modern theory. If quantum physics says information is never truly lost, and black holes look like they erase it, which rule bends? This tension is the black hole information paradox, and it hums softly beneath almost every conversation about horizons. Not all horizons are alike. The simplest solution, the Schwarzschild black hole, is the non-spinning, uncharged case. Add charge without spin, and you get the Reisner-Nordstrom solution. Add spin without charge, and you arrive at the Kerr black hole, the one nature seems to favor. Add both spin and charge, and the math writes down the most general stationary case called Kerr-Newman. The family resemblance is clear: an outer horizon that sets the point of no return, and a singularity within, where classical relativity admits it can no longer speak reliably. In the non-spinning case, that singularity is a point. In the spinning case, the singularity stretches into a ring in the plane of rotation, a geometry that tempts the imagination with tunnels and shortcuts. There are limits. Charge and spin cannot grow without bound for a given mass. Push either to its extreme, and you approach an extremal black hole, a state with special properties. Try to push beyond, and the equations suggest the horizon could vanish, exposing the singularity itself, a naked singularity, bold and unshielded. Most physicists believe nature forbids this, a principle called cosmic censorship, as if the universe keeps its most violent infinities modestly veiled. Simulations tend to agree. Real black holes, born from stars, probably carry little to no net charge and a healthy spin that stays short of the ultimate. The scale is both simple and staggering. Double the mass and the horizon's radius doubles. Shrink the mass and the radius pulls in. For a spinning or charged hole, the horizon sits a little closer than the simple Schwarzschild case, and the shape of the horizon itself flattens slightly at the poles, like a squashed sphere. When rotation is fast, spherical if still, oblate if twirling, another sign that even in extreme gravity, geometry remembers the common sense of spinning tops and planets. Time behaves like warm wax near these surfaces. Set a clock close to the hole and watch from far away, and you'll see it tick slower. This is gravitational time dilation, a soft stretch of seconds that lengthens into something nearly frozen as the clock approaches the horizon. Watch a falling object from the safety of distance, and it seems to slow, dim, redden, and then fade at the brink, never quite crossing in your view. The light it sends you loses energy climbing out, sliding toward red until the signal falls below your ability to detect. For the one who falls, the story is entirely different. No pause or shimmer marks the crossing. Local time runs gently forward. The horizon is not a wall, but a place where all outward paths end. Venture inward, in thought careful, but curious. In a non-spinning hole, tidal forces grow fierce. The gravity at your feet is stronger than at your head, and the difference stretches you, tighter and tighter, into a long thread, a process nicknamed spaghettification. Every object, if small enough to resist breaking early, meets the same thin fate before the final crush. In spinning holes, the geometry is more baroque. Equations extended past the safe zone hint at corridors and bridges, ring singularities with paths that might skirt the worst of the pull. They even whisper about closed loops in time world lines that return to their own past. But whispers are not reality. The consensus is that the slightest disturbance, the feeblest puff of dust or photon, collapses these delicate possibilities. Add quantum physics, a theory not yet fully married to gravity, and the exotic bridges are expected to crumble entirely. The insistence on singularities inside general relativity reads like a sign. Here the theory ends. Please build another. Some attempts at that new architecture are already sketched. One, from string theory, paints black holes as fuzzballs, no sharp horizon, no lonely point of infinite density, but a dense snarl of microscopic strings and brains whose average behavior mimics the smooth black hole we infer from afar. The details remain a frontier, but the theme is comforting. Replace the impossible with the complicated. Trade the infinite for the richly finite. Outside the horizon, light can do surprising things. There exists a precarious lane, the photon sphere, where a beam can circle the hole in a perfect ring. For a non-spinning black hole, this lies at 1.5 times the Schwarzschild radius. The orbit is exquisitely unstable. The slightest nudge sends the photon outward to freedom or inward to silence. In a spinning hole, this ring is not at a single distance. Prograde light moving with the hole's spin can orbit closer in. Retrograde light circles farther out. This unstable dance of photons is part of why black holes cast a shadow against glowing gas. Light from behind is bent around, piled up near these orbits, and carved away by the horizon, leaving a dark center with a bright, thin rim. The very image we've now seen. Spin deepens the strangeness. Around a rotating black hole is a region where standing still becomes impossible, even in principle. Space-time itself is being swept along, and you must move with it. This is the ergosphere, bulbous and squashed, touching the horizon at the poles and bulging outward at the equator. Inside, clever maneuvers can steal energy from the hole's rotation. In the Penrose process, an object splits so that one piece falls in and the other escapes. With more energy than it brought, the bonus paid out of the black hole's spin. With magnetic fields threading the maelstrom, an even grander theft occurs. The Blandford mechanism launching jets that spear outward from galaxy cores, bright and thin and seemingly endless. The black hole's darkness becomes, paradoxically, a source of cosmic brilliance. Closer in, orbits have a last safe harbor, the innermost stable circular orbit, or ISCO. Outside it, matter can circle like a planet. At the ISCO, a slight inward nudge unseats stability. Inside, no orbit exists that doesn't quickly decay. For a non-spinning hole, the ISCO sits at a fixed multiple of the horizon radius. For a spinning hole, the ISCO moves inward for matter that orbits in the same direction as the spin, and outward for matter going against it. Between the ISCO and the horizon lies the plunging region, a final slope where matter, having lost its foothold, rushes inward nearly at light speed. Heat and light blaze just outside the brink as the infalling gas releases the last of its binding energy. Beyond, all luminescence becomes memory. None of this contradicts the early plain idea. From far away, a black hole's pull is just gravity, measured and predictable. Draw close, and gravity becomes geometry's poetry, curving not only space, but time, thickness, and rhythm, and the order of cause and effect. That poetry explains the redshifts we see from the edges of accretion disks, the steady precession written in light, the timing of flares, the shape of shadows. It explains why two black holes with the same mass and spin behave as twins, even if their births were wildly different, one forged from a single star's collapse, another grown through 1,000 mergers. All the while, the old paradox murmurs, where does the information go? Stephen Hawking taught us that black holes are not perfectly black. Quantum effects near the horizon let them glow, faintly, with a thermal whisper. Over unimaginable spans, that whisper bleeds away energy. If a black hole evaporates, can its outgoing radiation encode the story of everything that fell in? Many believe yes, though the mechanism is subtle and the proof remains a prize. Perhaps the horizon is not the blank eraser it appears to be. Perhaps the surface degrees of freedom, whatever quantum gravity later names them, store and release the tail bit by bit, like embers giving back the heat they borrowed. Stand again by the lake in your mind. The air is still. Somewhere, very far from shore, matter circles a dark center, skimming the ISCO, brightening as it falls, a silver thread sliding inward. A few photons find the narrow path that bends around and escapes. Some trace the photon sphere and are jostled free, wandering to us across eons. Some fall and are gone from our sky. The black hole turns, and with its turning, space-time turns too, drawing out energy that streams away as a jet, like a lighthouse in a cosmic fog. The equations behind this scene are hard, but the picture they paint is tenderly consistent. A horizon that chooses silence, a surface that smooths detail into simplicity, and a core where our best theories ask for help. We lean into that quiet not to surrender, but to listen. Gravity speaks in curves, and those curves tell us that nature, at its most extreme, loves clean endings and long memory. Mass, spin, charge. A boundary that is soft to cross and impossible to return from. Light trapped in delicate loops, time stretched into honey. Somewhere, in the hush between stars, a black hole keeps watch, an absence with edges, a darkness with structure, while we drift, letting the mind's own horizon loosen, letting questions settle like dew on grass, trusting that what we do not yet know can still cradle us as we sleep. For a long time, the idea of black holes seemed more like a mathematical ghost than something the universe would dare to make real. Even Albert Einstein doubted them. He believed that when a star collapsed, its spin and momentum would stop it from shrinking endlessly, that nature would somehow protect itself from such extremes. Many physicists agreed. The equations hinted at these dark wells in space-time, but most scientists set them aside as curiosities, too strange, too final. Yet a few quiet voices kept insisting that the math was not a mistake. Step by step, they showed that nothing in the laws of physics actually forbade the creation of a black hole. By the end of the 1,960 seconds, the tide had turned. Roger Penrose proved that once an event horizon, a one-way boundary in space-time forms, Einstein's equations demand that a singularity must also exist inside. Stephen Hawking soon expanded that idea to the universe itself, showing that the equations describing the Big Bang also lead to singularities. Black holes were no longer exotic accidents. They were natural outcomes of gravity, doing what gravity does best. Meanwhile, other discoveries transformed these mysterious objects into something beautifully simple. The Kerr solution described rotating black holes. The no-hair theorem said that once a black hole settles, it can be defined entirely by three things: its mass, its spin, and its electric charge. And the laws of black hole thermodynamics revealed deep parallels between gravity and heat. What seemed impossible began to look elegant, even inevitable. The making of a black hole usually begins with a star at the end of its long, bright life. For millions or billions of years, The star's core burns steadily, balancing gravity's inward pull with the outward pressure of nuclear fusion. But when the fuel runs out, gravity wins. The star's heart collapses. Sometimes quantum pressure halts the fall, creating a white dwarf or a neutron star. But if the core is too heavy, beyond a few times the mass of our sun, nothing can stop the collapse. The result is a black hole. The most massive stars, those that begin their lives dozens of times heavier than the sun, end in spectacular supernovae, their outer layers thrown into space while the inner core implodes. In the very early universe, the first stars may have been far larger still. Their deaths could have left behind black holes hundreds or thousands of times heavier than our sun, the seeds from which today's supermassive black holes grew. Some astronomers even believe that, in the beginning, giant clouds of gas may have skipped the stage of star formation, entirely collapsing straight into enormous black holes. Those early monsters might explain the brilliant quasars we see shining when the universe was only a few 100 million years old. To an observer watching from far away, the moment of collapse plays out strangely. As matter nears the forming event horizon, time itself slows from the outside perspective. The falling surface appears to hover and fade, light stretching to red, vanishing into invisibility. It looks as if the star never quite crosses the boundary, but that is only an illusion. From the falling star's own point of view, the crossing happens quickly, quietly, without any special sign that the border has been passed. The idea of collapse is tied to density, but density alone isn't enough. Gravity needs a place to gather itself, a region of higher concentration to start the fall. In the young universe, space was thick with matter but also expanding rapidly, too quickly for gravity to pull everything together at once. Small ripples in density, tiny unevennesses in the early cosmos gave gravity a foothold. Over time, those ripples grew into galaxies, stars, and, in the right corners, black holes. Inflation theory, which describes the early burst of expansion after the Big Bang, suggests that a kind of repulsive gravity helped spread matter out, keeping the universe from collapsing back on itself. Collapse and expansion, two sides of the same cosmic coin. Though stellar collapse remains the main path to forming black holes, physics leaves room for other, rarer routes. In theory, if enough energy is squeezed into a small enough region, like in a high-energy collision, a black hole could briefly appear. The energies required are immense, far beyond anything we can reach on Earth. Some speculative theories propose that microscopic black holes might form when ultra-high energy cosmic rays strike the atmosphere, or even in particle accelerators like the Large Hadron Collider. But even if that were possible, they would vanish almost instantly, evaporating through Hawking radiation before they could interact with anything. The universe allows imagination to stretch farther than proof. Once born, a black hole grows by feeding. Gas and dust spiral inward, forming an accretion disk that glows brighter than stars as friction and gravity heat it. Sometimes, magnetic fields funnel part of that energy outward, launching narrow jets of plasma that shoot across light years. Whole galaxies can revolve around this exchange of darkness and light. Smaller black holes can merge, their horizons blending in a brief storm of gravitational waves, a cosmic vibration that travels across the universe, rippling space-time itself. When detectors like LIGO and Virgo caught those waves for the first time, we were hearing the sound of black holes colliding, a drumbeat from billions of years ago. Even Einstein's early doubts feel gentle now. He had worried that the equations described something too extreme to be real. But the universe seems to adore extremes. It makes them quietly, wherever conditions allow. The same geometry that describes a collapsing star also describes the expansion of the cosmos. The same equations that bend light around a black hole guide the paths of galaxies. What once looked monstrous has become a kind of order, nature's simplest shape for the most complicated forces. And so we have learned to live with the horizon. It's not a wall, but a turning point where what is known slips into what must be imagined. A black hole is gravity's deepest meditation, the point where matter stops pretending to be separate from space, where time curves so fully inward that past and future lose their usual meanings. Every galaxy carries one at its heart. Perhaps every story does, to a center we can't quite see, pulling everything toward stillness. If you picture it gently, it isn't frightening at all. It's a rhythm, expansion and collapse, burning and cooling, creation and return. The same laws that fold stars into black holes also hold the universe open. And somewhere in that balance between falling and flying, we drift, listening to the faint hum of gravity, the quiet sigh of matter letting go, the soft reminder that even in darkness, the cosmos continues to build. Sometimes, the universe grows not through creation, but through collision. Two stars may pass too close, their fates tangled, until one is torn apart. Two black holes may spiral together in silence for eons, their orbits tightening, the fabric of space-time trembling with every loop. Then, in one final instant, they merge two invisible hearts, becoming one. This quiet violence is how the cosmos builds giants. Many astronomers believe that the supermassive black holes anchoring galaxies were once smaller ones that found each other, fusing again and again until they became the colossal anchors of the universe. And yet, even black holes, those symbols of absolute darkness, are not truly black. In 1974, Stephen Hawking, blending the laws of quantum mechanics with Einstein's curved space-time, uncovered a remarkable secret. Black holes glow. The glow is faint, softer than soft, but it exists. Empty space, according to quantum theory, is never truly empty. It flickers with virtual particles that appear and vanish too quickly to notice. Near a black hole's horizon, these flickers can separate one particle escaping, the other falling inward. The result is what we now call Hawking radiation, a kind of cosmic sigh from the edge of nothingness. This discovery turned the idea of a black hole inside out. If they can radiate energy, then they can also lose it. Over vast timescales, they must slowly shrink, their horizons tightening like cooling embers. The rate of this evaporation depends on size. The smaller the black hole, the faster it fades. Tiny ones would blaze briefly, radiating intensely before vanishing in an instant. Larger ones would cool and quiet themselves almost completely. A black hole as heavy as our sun, for example, would be so cold, tens of billions of times colder than the universe around it, that it would gain energy from the cosmic background faster than it could lose it. In effect, it would feed instead of fade. Only black holes smaller than a mountain or much, much smaller than that could evaporate in any meaningful way today. A miniature one, no larger than a grain of dust, would vanish in a blink, its final moment releasing more light than 1,000 suns, but none have ever been found. Astronomers have searched for the telltale bursts of gamma rays that would mark the death of such ancient, primordial black holes. Space telescopes, like NASA's Fermi Observatory, keep scanning, waiting for that final flicker. But so far, the sky has kept its silence. If Hawking was right, then time itself is the slow undoing of every black hole. The small ones die young, the great ones fade last. A black hole with the mass of the sun would take an almost unthinkable 10 to the power of 64 years to disappear, a number so large that it stretches beyond imagination. The supermassive ones, the beasts at the centers of galaxies, would endure even longer, their lives measured not in years but in powers of eternity. And in the final, empty ages of the cosmos, long after the stars have burned out and galaxies have drifted apart, even these last black holes will whisper their final warmth into the dark. For now, we see them only by what they touch, the way their gravity bends light, the way they tug at neighboring stars, the way they ripple the universe itself when they collide. They remain invisible to our eyes, but not to our understanding. Their presence is written in motion, in light that bends and lingers, in the delicate trembling of space-time. Hawking's insight reminds us that even the darkest things can glow, that even in the deepest silence, the universe is still speaking. Think of Earth as a listening post on a quiet cliff, ears tuned to two kinds of whispers: light that curves and stalls near darkness, and the soft tremor of space itself when heavy things collide. From this lonely perch, we've learned to read black holes, not by looking at them, but by tracing the disturbances they leave in everything around them. One of the boldest ways we listen is with a telescope the size of a planet. The Event Horizon Telescope isn't a single eye, but a circle of radio observatories spread across mountains and deserts, linked together so their timing beats like one heart. By syncing recordings with atomic clock precision, this network turns Earth into a vast dish, sharp enough to sketch the rim of a black hole's shadow. When this global instrument aimed at the giant in Messier 87, a galaxy far out in the Virgo cluster, it watched for days, while the weather, the instruments, and the universe itself cooperated just enough. The picture revealed in 2019 wasn't of the hole no light comes from inside, but of a hot, bright ring of gas swirling at near light speed just outside the point of no return. A dark circle sat in the center, the shadow, carved by gravity so strong that even photons struggle to escape. The ring glowed unevenly, brighter on one side. That asymmetry is a gift of motion, Doppler beaming, where plasma moving toward us looks amplified and plasma moving away seems dim. The same physics explains why a siren sounds sharper as it approaches and lower as it recedes. Here, the sound is light itself, slanted by speed. Making that image of M87's heart was hard. Making the Milky Way's would be harder. Our own central black hole, Sagittarius A*, is much closer but far smaller, flickering faster than a camera can comfortably capture. Between us and the galactic core, clouds of charged gas blur radio waves like heat shimmer above a road. Still, in 2022, the same Earth-spanning telescope unveiled a second ring and shadow, Messier, softer but unmistakable, confirming that our galaxy, like so many others, keeps a silent anchor at its center. In polarized light, the EHT even traced magnetic fields threading the rim, the invisible rails along which charged particles are whipped and arranged. Gravity does more than sketch rings. It bends and braids light, acting as a lens. Near a black hole, light from the far side of the disk can wrap around and meet our eyes, letting us see a full ring when only half faces us. On larger scales, whole galaxies can lens background objects, stretching them into arcs. On the smallest scales, a lone compact mass drifting across our line of sight can briefly brighten a background star, a microlensing wink. After years of patient searches, astronomers have begun to spot such solitary black hole candidates through these winks, proof that some roam unaccompanied, dark and quiet, except for the way they bend starlight as they pass. Light is one messenger, the other is motion. For decades, astronomers have tracked the orbits of stars that whirl around the Milky Way's hidden center. One, known simply as S2, completes a tight, fast loop that would be impossible unless an enormous mass is confined to a tiny space. From these dances, we infer a central object with millions of solar masses tucked into a region far smaller than a solar system numbers, so extreme that only a supermassive black hole makes sense. The orbits don't just prove mass, they reveal relativity in action, showing a gentle drift of the ellipse, periapse, precession, exactly as Einstein's equations predict in strong gravity. Sometimes gravity speaks even more directly. In 2015, two compact shadows met in the dark and became one. Their merger sent ripples in space-time across the cosmos, and when those waves reached Earth, two giant L-shaped instruments, LIGO's interferometers, felt the universe change length by a fraction of a proton's width. It was the first clear sound of black holes colliding, a rising chirp as their orbits tightened, followed by a brief ringdown as the new horizon settled into its simplest shape. Since then, dozens of such signals have arrived, each one a storm recorded by instruments so calm that they can measure a distance change smaller than 1,000th of a human hair over kilometers of laser path. From the pitch and the way it fades, physicists read out masses and spins, even testing whether the newly formed black hole obeys the same tidy rules of simplicity that theory demands. Not all black hole stories are so grand. Many play out in close partnerships called X-ray binaries. In these, a normal star orbits a compact companion, sometimes a neutron star, sometimes a black hole. Gas drifts from the star toward the compact object and forms a glowing accretion disk. Friction and gravity heat the inner rings to such fierce temperatures that they shine in X-rays. If sharp pulses or surface signatures are detected, the companion is a neutron star with a solid surface. If the signals stay smooth and the mass estimate climbs above what neutron matter can support, the dark partner is a black hole. Cygnus X1 was the first strong candidate, a quiet early herald. Later, sources like V404 Cygni joined the list, flaring for months, then slipping back into quiescence, while astronomers used the lull to measure the companion's orbit precisely. In the fast flicker of these systems' quasi-periodic oscillations near the inner edge of the disk, physicists find additional clues because the frequency of that flicker leans on the mass and the spin of the compact object. Scale this feeding up, and you reach the extreme engines at galactic centers. When a supermassive black hole swallows steadily, its disk blazes across the spectrum, and narrow jets spear outward along magnetic field lines, nearly at light speed. These are active galactic nuclei quasars, and radio galaxies so bright that they can outshine all the stars around them. The standard picture here is simple but powerful: a central black hole, a hot disk, and polar jets. Observations across radio, optical, X-ray, and gamma ray bands keep filling in the details. while theory shows how spin and magnetic fields can draw rotational energy out of the hole itself, powering jets that reach far beyond their host galaxies. The brighter and busier the core, the more obvious the link becomes between the black hole's growth and the galaxy's history. A tight correlation, the M-sigma relation, ties black hole mass to the random speeds of stars in the galaxy's bulge, as if black hole and galaxy negotiated their growth together over billions of years. On quieter days, the evidence is subtler but no less persuasive. Some galaxies show stars shredded near their centers, tidal disruption events, brief fireworks that flare when a star wanders too close and is pulled into ribbons by tidal gravity. Part of the debris forms a temporary disk, lighting the core in ultraviolet and X-ray light before fading again. Elsewhere, thin rings of maser emission, natural microwave lasers in gas clouds, trace the warped disks around hidden giants, letting us weigh them with exquisite precision. Each method has its own blind spots and biases. Together, they converge on the same truth. The deep cores of galaxies harbor supermassive black holes, and many of the universe's brightest beacons are just matter falling inward, converting mass to light with ruthless efficiency. Black holes masquerade as other things only in our imaginations. Over the years, theorists have proposed exotic alternatives: gravastars, dark energy stars, other clever constructions that might mimic a black hole's exterior without hiding an event horizon within. It's healthy to test the obvious against the inventive. But the more we measure shadows that match the predicted size, ring-downs that ring at the right notes, stellar orbits that hug close without tearing, the more these alternatives struggle to fit all the data at once. Even a simple statistical fact nudges us toward acceptance. As black holes get bigger, their average density within the horizon drops. The largest ones are, on average, less dense than water. That counterintuitive detail makes them easier to grow from gentle, persistent feeding and harder to replace with unstable piles of dark, compact objects. Piles disperse, horizons endure. If you zoom back out, the picture is wonderfully consistent. We see the same ring and shadow geometry around two very different black holes, one monstrous and far, one modest and near. We hear mergers sing in gravitational waves, then fade into the tidy tones of a settled horizon. We watch stars loop the invisible at our galaxy's center and feel light bend as a dark traveler crosses in front of a distant source. We catch quasars at their brightest and X-ray binaries in their short tempers, both fueled by the same physics of disks and gravity, heat and loss. And through it all, the rules remain spare. Mass, spin, and rarely, charge set the stage. Magnetic fields supply structure. The horizon smooths away every fussy detail so the outside story stays simple. None of this breaks the quiet we've been keeping. If anything, it deepens it. Knowing how the picture was made, the stitched radio wavelengths, the synchronized clocks, the winters of calibration somehow makes the soft orange ring feel even calmer, like a candle seen through frosted glass. Hearing a merger as a brief rising note does not make the night any less still. It makes the stillness feel alive, threaded with meaning. We are small listeners on a small world, learning to hear the universe breathe. The breath is slow, the rhythm holds, and the darkness we once feared turns out to have edges we can trace, rules we can test, and a beauty that keeps unfolding, one careful observation at a time. Imagine a door that opens only outward. You can feel the warmth spilling through it, yet no matter how you push, you can never step inside. That is how physicists describe a white hole, the mathematical mirror of a black hole. Where a black hole swallows everything, a white hole lets nothing enter, but sends matter and energy flowing outward. It exists perfectly in Einstein's equations, though not, as far as we know, in the sky. White holes arise from the same mathematics that gave us black holes, the equations of general relativity. In the simplest eternal solutions, timeless universes that exist forever, a black hole lies in the future and a white hole in the past, two halves of a single geometry. But when scientists model real black holes formed by collapsing stars, the white hole part vanishes. The symmetry remains beautiful, yet nature seems to favor only one direction, inward. Still, the symmetry is irresistible. Both black holes and white holes could share the same traits: mass, spin, and charge, shaping space around them through gravity. The difference is in the boundary. For a black hole, once something crosses the event horizon, it cannot return. For a white hole, that boundary cannot be crossed from the outside at all. It is a one-way exit, not an entrance. In the maximally extended Schwarzschild solution, a kind of complete map of space-time, the past horizon of a white hole merges smoothly into the future horizon of a black hole. Space and time here curve continuously. There is no surface, only an infinite deepening of gravity toward a singularity where the known laws break down. These are elegant mathematical structures rather than physical objects. When quantum physics enters the story, the picture grows stranger. Stephen Hawking showed that black holes glow faintly through Hawking radiation, losing energy over immense timescales. In a perfectly balanced state, such a black hole could exist in thermal equilibrium, with its surroundings absorbing and emitting energy equally. Reverse time, and that same process would describe a white hole radiating outward instead of in. In this sense, black holes and white holes are two sides of one equation, connected by time's direction. The idea of white holes is not new. In the 1930 seconds, Robert Oppenheimer and Hartland Snyder studied Einstein's equations and glimpsed the possibility of their opposites, objects that might expel rather than consume. Later, John Leighton Synge hinted at the same symmetry, and in the 1960 seconds, Igor Novikov and Nikolai Kardashev developed it further. They found that in the full Schwarzschild geometry, two separate exterior regions appear essentially two universes connected by a narrow throat called an Einstein-Rosen bridge or wormhole. In this model, particles can fall into a black hole in one universe and emerge from a white hole in another. It's a poetic image, two worlds joined by a tunnel, one pulling in, the other spilling out. Yet the bridge cannot be crossed. Entering a black hole leads only to the singularity, not an exit. Approaching a white hole from the outside is impossible. The horizon acts as a perfect wall. The bridge exists only as a geometric connection, not a usable path. And it relies on the ideal of an eternal space-time that has existed forever, something the real universe does not provide. Because Einstein's equations are time-symmetric, they work equally well in reverse. It's logical to imagine a mirrored version of a black hole, a white hole born at the dawn of the cosmos, releasing energy until it fades away. But there is a problem. Real white holes would be extraordinarily unstable. The smallest disturbance, a single particle drifting too near, would disrupt their balance and cause them to collapse, turning them into black holes instead. The outward-only rule is too delicate for a noisy universe filled with dust and radiation. Even so, the concept continues to spark ideas. In some modern theories, a collapsing black hole might not end at a singularity. Quantum effects could create a bounce, transforming the implosion into an expansion, a rebirth as a white hole. In loop quantum gravity and string theory, this bounce appears as a kind of second act for dying black holes, where information that once fell in might eventually emerge again. These proposals remain speculative, but they point toward a deeper truth. The universe may never truly erase what it swallows. Thinking about white holes also clarifies why black holes behave the way they do. If black holes can radiate energy through quantum processes, then time symmetry demands an equivalent object that radiates naturally, the white hole. The fact that we never see one tells us something profound about how time itself may be asymmetric, favoring collapse over expansion, consumption over release. In diagrams of space-time, white holes help physicists understand the geometry around singularities, even if those singularities never form in reality. They are mirrors that show what gravity could look like if time were flipped. The elegance of the math reveals how thin the line is between falling in and pouring out, between a beginning and an end. There's also a humbling message buried in the theory. For black holes, horizons mark points of no return. For white holes, they mark points of no approach. Both boundaries exist because gravity and time weave together so tightly that cause and effect trade places. When we speak of the other side of a black hole, we may simply be whispering about a reflection, a version of space where time flows in the opposite direction. No telescope has ever glimpsed such a thing. No burst of light or fountain of matter has emerged to suggest a real white hole. If they ever did exist, they must have been born with the universe itself. Tiny explosions of energy that died in the first moments after the Big Bang. The math allows them. The sky does not confirm them. And yet, the thought lingers because it balances the story. Where black holes are endings, white holes are beginnings. Where one consumes, the other gives. In imagination, they form a rhythm that feels right. Inhale, exhale, gravity pulling in, gravity pushing out. If you picture one now, don't think of a violent eruption but a quiet pulse, a reversal of the black hole's silence, where light and matter drift outward as softly as mist. A universe that breathes, not in myth, but in mathematics, hinting that even its darkest places have opposites. Perhaps that is the quiet gift of the white hole, not proof of another world, but a reminder that symmetry can illuminate truth even when it never takes form. The mirror need not exist to show us what we are looking at. It's enough that it reflects what might be an elegant echo of time running the other way, glowing faintly at the edge of possibility. Try a different picture tonight. Not a door, not a bridge, just a hush in the air, the pause between an inhale and an exhale. In that pause, the equations of gravity lay out two complementary shapes. One curves every path inward, the other urges everything outward. We've met the inward one in the sky, the black hole, a deep well with a one-way rim. Its outward twin, the white hole, lives mostly on paper, an elegant echo drawn by the same mathematics, but rarely, if ever, invited by nature. Follow the math gently, and it shows varieties of this echo. For the simplest black hole Schwarzschild, the non-spinning, uncharged kind, the white counterpart, is a source that looks as if light and matter spring straight from the hidden singularity, the place where classical physics breaks. add charge, the Reisner and Nordstrom case, or spin, the Kerr case, and the sketch shifts. Now the outward fountain is not just a source in our exterior region. It reads like an exit door for something that fell into a black hole in a different exterior region, a separate outside, stitched to ours by the geometry. That stitch is the famous wormhole, a throat that seems to join two universes the way a tunnel joins two valleys, lovely to contemplate, treacherous to inhabit. Because even in these delicately drawn worlds, a rule refuses to bend. You cannot go into a white hole from the outside. Its boundary is sealed to incoming travelers. You may watch the outflow, but you cannot step through the skin. That sealed skin introduces a kind of unpredictability that makes physicists itch. If nothing outside can influence what happens within, the outward spray can look non-deterministic, as if the usual logic, cause here, effect there, has been cut. In practice, that's one more hint that the white hole half of the story is a mathematical reflection rather than a piece of working machinery. A separate, wilder creature lurks nearby. In theory, the naked singularity, an infinity of curvature, laid bare, with no horizon to hide it. A white hole is not that. The naked singularity has no keep-out boundary. The white hole does, but the keep-out door faces the wrong way. If you want a cosmic event that sits naked at the beginning of everything, the Big Bang comes to mind. Yet, even that comparison is slippery. Our cosmic beginning needn't match a white hole's strict rules. It's its own kind of mystery. Black holes, by contrast, have births we understand. A star lives, burns, and falls in on itself. Its heart collapses. A horizon forms. That history gives the black hole a timestamp. White holes show no comparable birth process. For one to exist, you'd need either a special formation mechanism the universe never seems to use, or an initial condition set at the first instant, a white hole already there at the dawn. Both options demand fine-tuning that nature tends to avoid. History shows how our ideas evolve when new light arrives. When astronomers first spotted quasars, lighthouses so bright they outshone their host galaxies, white holes were among the fanciful engines proposed. Maybe these were cosmic fountains, matter conjured from nowhere, radiating fiercely with no inward source. Observations later untangled the riddle. Quasars are powered by accretion, the fall of gas and dust into a supermassive black hole's disk, which heats and shines with ruthless efficiency. A simple gravitational engine fit the data. The white hole story stepped back into the library, and yet imagination kept playing, as it should. In the late 20th century and beyond, new sketches appeared. What if a collapsing star never quite pinches to an impossible point? What if quantum effects tiny to us, but enormous at unthinkable density, create a repulsive pressure that halts the crush and makes the core bounce? In the Einstein-Cartan-Sciama-Kibble approach, the spin of particles adds torsion to spacetime, producing exactly such a bounce at extreme density. Then the interior could unfurl, not into our exterior region, but into a newborn, hidden universe. From within that baby universe, the parent would look like a white hole, the sole bright mouth from which everything flows. In this tale, our own beginning could have been a gentle big bounce, not a singular explosion, a previous collapse reborn as expansion on the far side of quantum geometry. Other storytellers refined the thought. A shockwave cosmology suggested the Big Bang might be read as an explosion inside a black hole, the outer flow behaving like a white hole to its own domain. Another paper framed the bang as a small bang, a sudden pulse ejecting all matter in a blink. A few even tied odd gamma-ray bursts, brutally bright, very brief flashes to pop up white holes that appear and vanish almost instantly. These proposals are bold, fragile things. They give our minds traction, then politely bow to the data, which so far points to more grounded causes: merging neutron stars, failed supernovae, disks around newborn black holes. The thread running through all of this is symmetry. Einstein's equations don't prefer forward time over backward time. If you reverse a movie of the classical laws, the arithmetic still works. That symmetry is why white holes spring so naturally from the same math that gives us black holes. But the world we inhabit has an arrow of time, the slow spread of entropy, the drift from ordered to mixed, from hot to cool, from eggs to omelets. Black holes go with the arrow. Matter falls in, horizons grow. Information from an outside perspective is smoothed and hidden. White holes seem to push against that current. Matter sprays outward, from nowhere. Horizons shrink backward in time. Structure appears without an obvious ledger entry to pay for it. That mismatch doesn't forbid white holes in principle. It simply explains why the universe, messy and warm and busy, does not offer them up readily. Return to the wormhole for a moment, because it's too alluring to ignore. The maximally extended Schwarzschild map shows two exterior regions joined by a throat. The Kerr and Reissner-Nordstrom maps have even richer interiors with inner horizons and regions that resemble new exteriors. A traveler's tale suggests itself. Fall into one hole, emerge from a white twin elsewhere. But dynamical space-time is not a static diagram. Real collapse is not eternal. It has a before and after. Add a whisper of matter or radiation, any realistic disturbance, and the tidy throat pinches off. Quantum effects probably close it faster still. To keep a wormhole open, you need exotic stress energy, effectively negative pressure, of a kind we've not found in usable form. At cosmic scales, nature seems to prefer bridges you can draw, not bridges you can cross. So why keep the white hole in the story at all? Because it keeps us honest. It forces us to test each identity of the black hole against its mirror. If a black hole radiates by Hawking's logic, what would the time reverse look like? And why don't we see it? If information can be preserved in some subtle, quantum way across a horizon's life, what might the time reverse say about how structure emerges? These questions don't require white holes to exist. They require us to understand why their mirror sheen doesn't show up in the sky. On the observational side, the ledger is stark. We have seen the shadow of a black hole framed by incandescent gas. We have heard the chirp of two horizons becoming one and the ringdown that follows, a bell tone in space-time. We have mapped stars slingshotting around the quiet heart of the Milky Way, their orbits hugging mass that cannot be anything but a supermassive black hole. We have watched flares that match tidal shreddings of stars at galactic centers, and we have weighed dark cores with maser rings like rulers. For white holes, we have mathematics and metaphors. No persistent fountain with a sealed rim. No source that cannot be approached. no flash that must be a white hole rather than some wilder version of the engines we already know. Still, the white hole thought experiment continues to earn its keep. It highlights how sensitive horizons are. A black hole's rim is a future boundary. Cross it, and every future path leads inward. A white hole's rim is a past boundary. Approach it, and every past path leads outward from within. Flip the arrows and you flip which slices of space-time are accessible. That flip clarifies why even tiny perturbations spoil the white hole solution in a living universe. Dust, photons, cosmic rays, ordinary clutter push the geometry off balance. The inward door tolerates clutter. The outward door does not. The same sensitivity colors naked possibilities. If an interior singularity is truly exposed, no event horizon to hide it, the equations lose predictability for outside observers. Almost everyone expects quantum gravity to cure such singularities, replacing infinite with complicated. Loop quantum models, string-inspired microstate geometries, and other candidates try to do exactly that. In some of those cures, a bounce or an effective white hole-like phase appears, not as a permanent, pristine fountain, but as a transient passage through extreme curvature. The mirror returns again as punctuation, not as punctuation mark. A few astronomers keep testing the skies for signatures that would make the white hole camp harder to dismiss. Could an unusual gamma ray burst with no afterglow and no host galaxy be a candidate? Could an orphan flare in a dark patch of sky betray a brief, outward-only pulse? So far, every intriguing hint has found a more ordinary home. Mergers, magnetars, messy disks. The search is still useful. If nothing else, it sharpens our sense of what extraordinary would have to look like to overturn the current inward-leaning story. Through all of this, it helps to carry a gentle metaphor. Black holes are like eddies in a slow river, turning leaves inward and down. White holes would be the hidden springs that push water up through sand, unfurling ripples outward that no swimmer can push against. Rivers have eddies everywhere. Springs are rarer and finicky. In the cosmos, the gravitational equivalent holds. Collapse is common. Sealed outward fountains are not. None of this is a rebuke to curiosity. It's an invitation to wider balance. The symmetry that creates white holes in our equations is real, and it illuminates where our understanding is shallow, near singularities, across horizons, at the edge where quantum and gravity meet. The arrow of time that seems to reject white holes is real, too, and it reminds us that the universe prefers processes that spread and mix. Between symmetry and arrow, between mirror and motion, we find the path that observation walks, rings of light that match predictions, waves in space-time that arrive on cue, stellar dances that weigh invisible anchors. If, one night, the sky does offer a different kind of flare, brief, perfect, unapproachable, our picture will widen and the mirror will step closer to the window. Until then, the white hole remains a useful whisper, a way to ask better questions about black holes, a way to keep time's two directions in mind while we drift along the one we know. Breathe with that thought. Inward pull, outward dream. The equations allow both. The universe seems to choose one. And in that asymmetry, strange as it is, there's a calm kind of clarity, like listening to the ocean and noticing that, for all the talk of the tide, it's the steady hush between waves that helps you fall asleep. Imagine a quiet field at night after rain, the ground breathing a faint mist. Somewhere under the soil, springs push gently outward, while nearby, a sinkhole draws water down. General relativity gives us versions of both. We've learned to recognize the sinkholes, black holes, by their shadows, their hot rings, their songs and gravitational waves. The springs, the white holes, are the mathematical counterpoint, outward-only sources with sealed horizons. Where might such outward springs appear if the universe ever allows them? The first place to look is the beginning. Wind the cosmic clock back to the first fractions of a second, and the universe is a storm of heat and density where familiar rules wobble. Space and time themselves jitter. Matter and radiation churn. Tiny quantum fluctuations are written into the fabric, like seeds in fresh loam. In that chaos, some theorists imagine brief, outward-only eruptions, white hole-like pulses flaring and fading almost at once. If they existed, they'd be primordial, born alongside the first light, too short-lived to persist, but perhaps loud enough to leave traces in how matter later clumped. That clumping our cosmic web of filaments and voids is one of the great pattern stories of the early universe. We know gravity amplifies small differences into large structures, but the speed with which order appears still invites questions. A sprinkling of early outward bursts could, in principle, salt the sky with unusual seeds, nudging the web's growth. It's a poetic idea that remains unproven. Observations of the microwave background, galaxy surveys, and simulations already explain much of the web without calling on white holes. Still, the door stays cracked open. If rare anomalies in early structure were found, one could ask whether a handful of fleeting outward sources helped sculpt them. A second possible birthplace is much smaller, the scale where quantum foam fizzes. At tiny distances and blink-fast times, energy sloshes in and out of existence as particle-antiparticle pairs, a restless background hum. If space can briefly mint particles from its own fluctuations, could it also mint micro-white holes, tiny outward sputters smaller than atoms, appearing and vanishing before they can be greeted? Some treatments of quantum gravity play with exactly that. The analogy here is with primordial black holes, another speculative population that might have formed from dense patches in the young universe. If black specks were possible then, perhaps white specks were too short-lived and rare, more whisper than shout. Even a hint of such micro-events would be meaningful. It would show that white holes are not just mirror paintings, but occasional products of the same laws that govern everything else. People sometimes stretch the idea further and ask whether oddities we ascribe to dark matter might be explained by unusual, compact objects. Primordial black holes are the usual suspects, but you'll find white holes in those speculative lineups as well. So far, careful counts of microlensing events and other effects make abundant white holes an unlikely explanation for the dark matter puzzle. The picture might change with new data, but for now, the night's extra gravity seems better matched to something more uniform and quiet. The third place to look grows directly out of the mathematics that pairs inward wells with outward fountains. In the simplest, maximally extended Schwarzschild solution, a black hole on one side of the page is shadowed by a white hole on the other. Geodesics, natural paths of light and matter can emerge from that white region into an exterior like ours. Add charge or spin, and the architecture becomes ornate. Inner horizons, multiple regions, staircases of outsides, connecting in unexpected ways. In these diagrams, a black hole and a white hole are two faces of a single sculpture, joined by a throat, a wormhole that seems to promise a route from infall to outflow. But the statue is made of math, not mortar. Real black holes form at specific times from collapsing matter. They are not eternal crystals hung in empty space. Introduce that realism, add in falling gas, radiation, the ordinary clutter of a live universe, and the pristine throat pinches shut. You cannot step into a white hole from outside. You cannot survive the singularity inside a black hole to emerge elsewhere. Keeping a wormhole open requires exotic stress energy, effectively a kind of negative pressure we have not found in bulk. So while the extended map teaches us what symmetry allows, it does not grant us a working bridge. The question of stability keeps returning. A black hole's horizon is a future boundary. Once you cross, all futures point inward. A white hole's horizon is a past boundary. From outside, every possible past for a point near it comes from inside. Flip the time arrow, and you flip which side of the border matters. That very flip is what makes outward-only horizons so fragile. Our universe is not a sterile stage. It is full of stray photons and dust and plasma. The tiniest bit of incoming disturbance should spoil a white hole's delicate balance. If one ever flickered on, the first tap from the world around it would upset the symmetry and snuff the outward flow. That's why many physicists doubt large white holes can survive in the modern sky. And yet, the mirror remains useful. It clarifies how black holes might end. Stephen Hawking showed that horizons glow faintly. As time stretches, that glow saps a black hole's mass. For stellar and supermassive holes, the evaporation time is wildly longer than the age of the universe, so we have never watched one finish. But if you extrapolate the math to the final moments, some models predict a brief, violent release. In that instant, the decaying horizon behaves white hole-ish, an outward surge of whatever can be radiated, a last exhale. If such end bursts exist, they happen on timescales beyond any human or planetary patience, but they remind us that the inward story may someday have an outward coda. Now and then, possibilities are sketched that push white holes closer to the middle of the stage. Loop quantum gravity, which treats space as woven from discrete loops, often replaces singularities with bounces. In those pictures, matter falling in compresses until a quantum pressure pushes back and the interior re-expands into a white hole-like region. To outside observers, the black hole lives its very long life. To interior observers, time is warped, so the bounce and re-expansion can happen quickly by their own clocks. Similar ideas pop up in string-inspired microstate models, where the classical black hole is replaced by a complicated, horizonless object whose collective behavior mimics an ordinary hole from afar. In some of those microstates, outward channels might appear without true event horizons. None of these proposals are confirmed. Their value right now is as laboratories where the rules of quantum and gravity can meet without infinities. If you follow the bounce thread to its wild end, a haunting question emerges. Could our entire universe be the inside of a white hole? The Big Bang has often been compared to a white hole because it is an outward-only boundary in our past. You cannot go through it from our side. Everything emerges from it. Some speculative models sharpen that into a claim. A parent universe's black hole interior becomes our white hole-like beginning. Our arrows of time and entropy grow from that inherited boundary. It's an elegant loop that cannot yet be tested, but it keeps alive the idea that beginnings and endings may be different sides of one process viewed from different vantage points. If white holes exist, how long would they last? Here again, the inward-outward contrast dictates the answer. Black holes can survive for eons. Feeding makes them grow. Only Hawking radiation eats them away, and that takes forever by any human clock. White holes cannot eat. Once they have vented their store, they vanish unless a theory grants them a sustainable internal engine. Most do not. The result is a likely population, if any, of short-lived events, bright, brief, and rare, easy to miss unless you are looking across the whole sky all the time at the highest energies. That brings us to fireworks. Gamma-ray bursts are the most violent flashes of light we've recorded. Some last fractions of a second, others linger for minutes. We can account for most of them, with known engines merging, neutron stars, collapsing massive stars, but a few remain peculiar. A minority of physicists has wondered whether an odd, hostless burst or two might be white hole candidates, outward-only flares in the quiet suburbs of the universe. So far, nothing has required that interpretation. Instruments like Fermi and Swift continue to scan. A truly unclassifiable flash would at least revive the conversation. There's also the deeper ledger, information. Quantum mechanics insists information is not destroyed. A black hole's hunger seems to erase it behind the horizon. This tension is the black hole information problem. If, at the end, a black hole's decay mimics a white hole's exhale, perhaps the long, subtle radiation encodes the story of what fell in. From that perspective, the white hole is less an object than a phase, a way information might return to the world. Whether the coding works through delicate correlations in Hawking radiation, through holography, or through some bounce-like release is exactly what modern theory is wrestling with. All of these possibilities sit on a foundation laid by Einstein's field equations: gravity as geometry, mass and energy as the ink that shapes space-time's lines. Those equations are time-symmetric. They do not prefer inhale to exhale. The universe does. Entropy climbs, eggs scramble, stars spend their fuel, horizons grow. Black holes are friendly to that arrow. White holes aren't. That's the quiet reason the sky has given us shadows and rings and chirps from inward wells, but no fountains we cannot approach. It doesn't mean the mirror has no role. It keeps our imaginations lit and our logic sharp. It reminds us to check which features of a black hole owe their existence to time's arrow, and which belong to the geometry itself. It nudges us to think in pairs: collapse, expansion, trap, fountain, hidden, visible, memory, forgetting. It pushes quantum gravity to replace impossible points with difficult details. And it suggests concrete targets to watch for: brief, intense, unapproachably outward flares, odd timing patterns that defy inward engines, relics in the early universe that demand a one-way source. If you want a picture to hold while you drift, take this one. Far out in intergalactic dark, a black hole slowly feeds from a thin ring, its light bent into a lopsided halo, its spin dragging space like a spoon stirs tea. Somewhere in the mathematics tied to that same scene, a twin exists, a horizon that only gives. In our world, the twin is a sketch pinned to the chalkboard. In some deeper future understanding, it may be a transient phase or a memory of a beginning. For now, the sky chooses the inward door. The outward door stays as possibility, a way to test what we think we know, a reminder that symmetry is generous, and a gentle reassurance that even unanswered questions can be soothing when they put the universe's edges into view. Across the vast canvas of space, there are places where everything we know about light, matter, and time simply gives way. Black holes, once nothing more than equations written in the margins of Einstein's notebooks, have become undeniable. We've seen their fingerprints in the X-rays of dying stars, traced their gravitational pull through the dance of nearby suns, and even captured their shadows glowing like dark halos around distant galaxies. White holes, on the other hand, remain pure theory, the quiet reflections of their darker twins. No telescope has ever caught their light. No faint whisper of their presence has rippled through space-time. Yet mathematically, they belong to the same family as black holes, written into the same elegant geometry of Einstein's general relativity. If black holes are cosmic graves, white holes are their mirrors, fountains instead of traps, beginnings instead of endings. This strange symmetry becomes even more mesmerizing when you follow it deeper into the tunnels of the mind that Einstein and his colleague Nathan Rosen once explored. In 1935, they noticed that under certain conditions, the equations of general relativity could link two regions of space and time through a kind of bridge. They called it an Einstein-Rosen bridge. We now call it a wormhole. Imagine space not as emptiness, but as a fabric that can fold. If you wanted to cross from one edge of this fabric to the other, you could crawl across the surface for light years, or you could fold it so that the edges touch, punching a tunnel straight through. A shortcut through the very structure of space-time. In theory, one mouth of this tunnel could open at a black hole, and the other at a white hole. What falls into the black hole might one day spill out from its luminous twin somewhere else, perhaps even in another universe. It's an idea that has inspired decades of science fiction and philosophical wonder, but in physics, the reality is less forgiving. The equations say wormholes would be terribly unstable, collapsing faster than anything could pass through them. To keep one open, nature would need a kind of exotic matter with negative energy density, something that pushes instead of pulls, a property no known substance possesses. Quantum mechanics hints that such negative energy might flicker briefly into existence, but not in the sustained, cosmic way a stable wormhole would require. Even so, the concept holds power because it forces us to ask, what is possible? Einstein's equations are not the imaginings of poets. They have been tested again and again in the bending of starlight during a 1919 eclipse, in the slow ticking of clocks on orbiting satellites, in the ripples of gravitational waves, first heard in 2015. The same mathematics that predicted black holes also leaves room for white holes and wormholes, as if the universe itself insists on symmetry for every abyss, a source, for every end, a beginning. To understand this balance, we must face the heart of the matter, the singularity. A singularity is where gravity grows infinite, where the fabric of space folds into itself so tightly that all known laws break down. Inside a black hole, that singularity sits hidden in the future. Everything that falls in is drawn toward it, never to return. In a white hole, if one could exist, the singularity would be, in the past, a primordial eruption, spitting energy outward. Some cosmologists have even suggested that our entire universe began this way, that the Big Bang itself was the birth cry of a colossal white hole. It's a poetic image, a universe erupting from the other side of some unseen throat of space. Yet the original Einstein-Rosen bridge doesn't last long enough for anything to pass through. The tunnel pinches off almost instantly, in the 1,950 seconds and 1,960 seconds. Physicists like John Wheeler, the man who gave black holes their name, began to wonder whether such structures could ever be stable, perhaps even traversable. Could gravity, in its most extreme form, create hidden corridors through reality itself? These were questions for mathematics to chase, but the telescopes began to answer the rest. As technology advanced, astronomers found black holes everywhere, small ones, only a few times heavier than our sun, and giants, millions or billions of times more massive, sitting quietly in the hearts of galaxies. Our own Milky Way harbors one of these giants, Sagittarius A*, about 26,000 light-years away. In 2019, the Event Horizon Telescope released an image of another, a glowing ring around the shadow of the black hole in the galaxy M87. What had once been a theoretical curiosity became a cosmic fact. White holes, however, remained untouched by observation. They exist only in the mathematics, yet their presence there is meaningful. They remind physicists that Einstein's equations do not favor one direction of time over the other. On paper, the universe can run forward or backward, and the laws hold true either way. So why, in our lived experience, does time only move forward? Why do stars burn and not unburn? Why do we remember yesterday and not tomorrow? This mystery of the arrow of time is woven tightly into the story of black and white holes. A black hole fits neatly with the arrow, swallowing matter and increasing disorder or entropy in the universe. A white hole would do the opposite, releasing matter and decreasing entropy, a kind of local reversal of time itself. For that reason, most physicists doubt they could exist in a universe like ours, where the arrow of time is so firmly set. Yet in the equations, they are unavoidable, the mirror partners of black holes that whisper, "What if?" Stephen Hawking's work in the 1,970 seconds brought new life to the question. He discovered that black holes aren't perfectly dark. Quantum effects at the event horizon cause them to emit faint radiation, now called Hawking radiation, over unimaginable spans of time. This radiation causes a black hole to lose mass, shrinking until it vanishes. Some theories suggest that the final flash of its death could look like a tiny white hole, a last, bright release of all it had devoured. In this picture, black holes and white holes are not opposites at war, but stages of a single cosmic life cycle collapse, stillness, rebirth. To imagine this is to see nature's balance written across every scale. Stars die to create the elements that form new worlds. Forests burn so that seeds can sprout. Even here on Earth, endings feed beginnings. Think of the monarch butterfly. It begins as an egg, becomes a caterpillar, dissolves into itself inside a chrysalis, and then unfolds again into wings. The black hole is the chrysalis, dense, dark, secret. The white hole would be the moment of flight, the sudden release into light and motion. Nature loves such mirrors. Consider the sea turtle, returning each generation to the same beach to lay her eggs. For the hatchlings, the frantic dash to the sea is a white hole moment, a burst into the unknown. For many, the vast ocean becomes their black hole, swallowing them into its depths. Yet across millennia, life endures, the pattern repeating endlessly, endings and beginnings braided together like waves on a shore. Scientists often turn to these metaphors not to soften the facts, but to make them graspable. The truth of relativity is vast and abstract, yet the rhythm of its ideas can be felt in the world around us. A black hole might be compared to the deep-sea anglerfish, glowing faintly in darkness and devouring what comes too close. A white hole could be like the bombardier beetle, which releases hot bursts of chemicals to drive danger away, a one-way fountain of energy. A wormhole, perhaps, resembles the journey of the Arctic tern, the small bird that travels from pole to pole every year, carving impossible shortcuts across the globe as if it knew some hidden geometry of its own. Such comparisons remind us that the universe's extremes are not foreign to us. They are continuations of patterns we already know. Einstein's mathematics, drawn on paper more than a century ago, opened a door not just to the heavens, but to the very idea of reality as flexible, continuous, alive. He redefined gravity not as a force pulling objects together, but as the bending of space and time themselves. In his picture, matter tells space how to curve, and space tells matter how to move. From that elegant dance emerged predictions so wild that even Einstein doubted them at first. Predictions that would one day describe the invisible engines of galaxies. The discovery of black holes reshaped modern astronomy, but the persistence of white holes keeps the conversation philosophical. They challenge our comfort with one-way time, with irreversible loss. If something can fall forever into a black hole, can anything ever come back? The equations say it might. They hint at a deeper symmetry, perhaps hidden behind the walls of what we can see, a universe that breathes in and out across the ages, each collapse paired with a release somewhere else. Time's arrow, for all its certainty, may be only a local illusion. Entropy increases here, in our small corner, but the cosmos may be far more intricate than our clocks allow. What we call beginnings and endings may simply be changes in direction, like the turning of tides or the shifting of seasons. Across cultures and centuries, humans have told stories that echo this same pattern. Myths of death and rebirth, destruction and creation, descent and return. The scientific language of relativity gives those myths a new vocabulary. Black holes as the cosmic abyss, white holes as the fountains of renewal, wormholes as the hidden roads between. Physics and poetry meet here, both reaching for what lies beyond understanding. When you look up into the night sky at the faint spill of the Milky Way, at the ancient light from stars long gone, you're looking at time stretched thin. Somewhere in that fabric, unseen, a black hole may be quietly swallowing starlight. Somewhere else, in the equations at least, a white hole may be shining in answer. We have evidence for one side of the mirror. The other remains an idea, shimmering just beyond reach. Perhaps that is where it belongs, at the edge of knowledge, where science and wonder share the same breath. Black holes remind us of how small we are. White holes remind us of how much remains possible. The universe, vast and unfinished, still holds room for both. And as we drift through it, we too become part of that symmetry, creatures of gravity and light, falling and rising, endings and beginnings, intertwined in a story as old as time itself. Let the mind settle, like steam fading from a warm cup, and listen to the soft rule that hums beneath everything, the world's quiet habit of loosening. Physicists call it the second law of thermodynamics, but you've known it since childhood. Ice melts, batteries drain, a tidy room drifts toward clutter, unless someone tends it. Entropy is the quiet current that runs beneath everything. It isn't loud or cruel, just patient. Ice melts, metal rusts, stars burn and fade. The second law of thermodynamics gives this slow unraveling its name. In any isolated system, disorder or entropy always grows. Energy spreads, order loosens. A log turns to ash and smoke. The heat drifts into the air. What was neat becomes mixed. That drift toward chaos is not failure, it's the rhythm of the universe itself. Black holes fit naturally into that rhythm. They are the great collectors of entropy. Drop matter or light into one, and all the details of what fell are erased. Only mass, spin, and charge remain. For decades, physicists thought that was the end of the story, that black holes swallowed and kept, without returning anything, to balance the cosmic books. Then, in the 1970 seconds, Jacob Bekenstein proposed something daring. Black holes must have entropy of their own. If you drop something messy into one, the universe's total disorder shouldn't decrease. The whole itself must grow more disordered. Stephen Hawking followed with a deeper shock. Black holes glow faintly. Quantum effects make them radiate a thin, cold light, now called Hawking radiation. That faint heat means temperature, and temperature means entropy. A black hole's entropy isn't measured by its volume, but by the area of its event horizon, the invisible boundary beyond which nothing returns. This was one of modern physics' strangest and most beautiful revelations. Gravity, thermodynamics, and quantum theory all whispering the same truth. But if black holes embody entropy's growth, what about their opposites, the white holes? These hypothetical twins would do the reverse. Nothing could fall in, and matter and radiation would only pour out. A white hole would be a cosmic fountain, a radiant storm of particles flowing outward endlessly. The question that follows is unavoidable. If such a thing existed, would it break the second law? In relativity's equations, time can run either way. Run them backward, and a black hole becomes a white hole. But nature rarely honors perfect reversals. Time has a direction, the arrow that points from order to disorder. We see eggs break, not unbreak. Smoke rise, not fold back into the fire. White holes seem to demand that reversal, gathering disorder into exact patterns, as if the universe were playing its film backward. That's why they feel so unnatural. Some physicists argue that a true white hole would indeed violate the second law. For its outflowing particles to be so perfectly arranged, its entropy would have to shrink, meaning the universe becomes more ordered. That would make a white hole a region where time runs backward, an island of reverse history. Others suggest the picture is subtler. Entropy is not local, but global. If white holes exist, they might simply complete a cycle that keeps the total disorder of the cosmos rising overall. Imagine, for example, that every black hole eventually becomes a white hole. As Hawking radiation drains its mass, the black hole shrinks. Near the end, rather than vanishing, it could rebound, space itself bouncing at the smallest scale, converting the implosion into an explosion. Everything swallowed over its lifetime would spill back out in a final burst. Entropy would not fall, because the long process of growth and evaporation would still outweigh that last release. The second law would remain intact. This vision connects with loop quantum gravity, a theory that tries to unite Einstein's space-time with quantum mechanics. It imagines that space and time come in tiny, indivisible grains a geometry made of atoms too small to see. In that world, collapse does not lead to an infinite singularity, but to a bounce, a reversal of compression. A white hole could simply be the outward face of that rebound, the other half of a black hole story. Yet the puzzles remain. What is the entropy of a white hole? Black holes carry entropy proportional to their horizon's area, but a white hole doesn't absorb anything. Does it inherit its twin's disorder, or does it start fresh? Some theorists suggest that a white hole keeps the information of the black hole that birthed it, releasing it later in a scrambled flood. That idea links to the black hole information paradox. When something falls in, is its information lost forever? Hawking once said yes, then later changed his mind. If information always reappears, perhaps through a white hole's last burst, then thermodynamics is saved and the cosmic record stays whole. To picture the challenge, think of spilling coffee. The liquid spreads, staining the floor. That's entropy rising. A white hole would be like the stain collecting itself, drop by drop, leaping neatly back into the cup. Not impossible, just impossibly unlikely. The second law doesn't forbid reversals. It only says they are fantastically rare. The odds of a warm room's water freezing spontaneously are so small that the universe would age and die before it happened. A white hole might be that kind of rarity allowed by mathematics, rejected by probability. Entropy's arrow depends on beginnings. Our universe started in astonishing order, a low entropy state after the Big Bang. From that point, disorder has been climbing ever since. If the cosmos had begun already disordered, time might feel directionless. White holes might not seem strange at all. Some scientists even suggest that the Big Bang itself was a white hole of cosmic scale matter and energy erupting outward from a single point, nothing entering, only expanding. If so, we are living in the long aftermath of that first and greatest white hole, and it didn't break the second law because it set the arrow of time we follow. Numbers give the same lesson in starker terms. A black hole, the mass of our sun, has an entropy of roughly 10^77, an almost unimaginable amount of disorder. When a star collapses, its entropy skyrockets. The law approves, but if such a hole were to reverse into a white hole and eject its contents neatly, entropy would plummet, breaking the rule. Only if the final eruption is chaotic, spewing particles in random patterns, does the balance hold. In that case, the white hole adds to the universe's messiness instead of undoing it. Computer models suggest that near the smallest possible scale, around 10^-35 meters, a black hole might end in a burst of pure chaos, a flash of energy, unstructured and wild. From far away, it would look like a cosmic firework, a brief bloom of radiation that increases, not decreases, disorder. The law would stand unbroken, and yet no telescope has ever seen a white hole. We've found black holes in colliding galaxies, heard them merge through gravitational waves, even photographed their shadows. White holes remain purely theoretical. Some astronomers have speculated that certain short gamma-ray bursts might be their dying breath, but so far, the evidence points elsewhere. Perhaps that's to be expected. The second law rules by statistics, not absolutes. It doesn't forbid a glass from unshattering. It simply makes the odds so poor that the event is, for all practical purposes, impossible. White holes may be the same mathematically possible, physically improbable beyond reason. The universe could allow them in principle, but almost never in practice. Even if one did appear, it would be fragile. A white hole cannot accept incoming matter. Yet, the cosmos is full of stray dust and photons. The slightest touch might disrupt it, turning it unstable, collapsing it back into darkness. It would be a delicate thing in a rough universe, like a soap bubble rising through a storm. So the story returns to its quiet center. Entropy still flows forward. Stars still fade. Energy still spreads thin. Black holes may one day dissolve into light, their endings transforming into scattered beginnings. If white holes exist, they are not violations of the law but echoes of its reach, moments where the universe exhales the disorder it has already earned. The second law remains undefeated. It's the pulse that keeps time moving one way, the cosmic preference for the mixed over the pure, the diffused over the concentrated. White holes, whether real or only imagined, do not escape that tide. They would only join at flares of release, in a universe forever softening, forever loosening its hold, forever drifting toward the next quiet spread of heat and silence. Imagine space itself humming, not with sound but with motion, ripples passing through the fabric of reality. Somewhere in the dark, two enormous black holes circle each other, closing the distance until they merge. The impact shakes space-time, sending gravitational waves across the universe. When those waves reach Earth, our detectors tremble ever so slightly less than the width of a proton, and yet within that tiny shiver may lie the first clues to something deeper than Einstein's gravity, the long-sought quantum nature of space-time. Gravity has always felt familiar, but its foundations remain mysterious. Newton gave it shape. Einstein gave it depth. His theory of general relativity explains gravity as the bending of space and time around mass and energy, a smooth, continuous fabric. Quantum mechanics, however, rules the microscopic world with jitter and probability. Combine the two, and they rebel. Somewhere between them must lie a deeper law, quantum gravity, a description of how space-time itself behaves when pushed to its limits. Black hole collisions are nature's laboratories for testing those limits. Our most powerful machines, like the Large Hadron Collider, reach trillions of electron volts. But two colliding black holes release energies beyond comprehension, billions of times greater, pressing physics to the edge of what it can explain. When LIGO first detected gravitational waves in 2015, it confirmed Einstein's prediction and opened a new window to the cosmos. Each detected wave is now more than a discovery. It's an experiment performed by the universe itself. The detectors listen the way elephants feel thunder through vibrations. As two black holes spiral together, the waves rise in pitch and strength, peaking at the instant of merger before fading into silence. This final echo, the ringdown, is a fingerprint of the merged object. General relativity predicts its pattern precisely. Yet, if quantum effects alter the structure of black holes, the sound may change, a faint shift, a stutter, an echo out of place. Relativity says that a black hole hides a singularity at its center, a point of infinite density where known physics breaks down. But infinities are the universe's way of saying, you've gone too far. Quantum gravity might smooth them out. Perhaps, deep inside, space folds into a quantum core or opens into a wormhole. If so, the waves from merging black holes could carry a subtle signature of that difference. Physicists study these tiny ripples, called quasi-normal modes, with the precision of a watchmaker listening for a missing tick. Some ideas suggest that the event horizon, the invisible boundary from which nothing escapes, is not perfectly smooth. Quantum fluctuations could wrinkle it, forming energetic firewalls or tangled fuzzballs. If such structures exist, merging black holes might produce faint echoes in the gravitational wave signal, as though the ringing waves bounced off irregular surfaces before escaping. No one has confirmed such echoes yet, but researchers continue to listen. Neutron stars offer another kind of test. These collapsed stellar remnants pack more mass than the Sun into a sphere only 20 kilometers wide. When two of them merge, they create both gravitational waves and light gamma rays, X-rays, visible flashes. The event observed in 2017 proved that such collisions forge gold and other heavy elements. But it may also hold traces of quantum gravity. If space-time behaves differently at extreme densities, the timing and shape of those waves could betray it. The search is delicate. Gravitational waves are faint, easily buried in noise from earthquakes, ocean tides, or even traffic. Detectors must be isolated, their mirrors suspended on perfect vacuums, their signals filtered through miles of code. The process demands patience. Physicists sift through mountains of data the way pangolins dig for hidden ants, slowly, persistently, guided by instinct and method. Why such effort? Because finding quantum gravity would complete a century-old quest to unite the laws of the large and the small. Einstein's equations describe the cosmos, while quantum mechanics governs atoms. Somewhere at the Planck scale, around 10 to the power of -35 meters, they must meet. Some theories imagine space woven from tiny loops of geometry. Others propose vibrating strings in higher dimensions. None are proven, but the collisions of black holes may leave fingerprints strong enough to decide among them. Future observatories promise sharper hearing. Ground-based detectors like Cosmic Explorer and the Einstein Telescope will sense more distant mergers with unprecedented clarity. The space-based LISA mission, launching around 2035, will listen to deeper, slower waves from supermassive black holes, millions of times heavier than the Sun, whose mergers sculpt the cores of galaxies. Meanwhile, pulsar timing arrays, networks of radio telescopes tracking the steady beats of neutron stars, are beginning to detect a background hum of gravitational waves that fills the universe like ocean swell. Together, these instruments are giving humanity a new sense, not sight, but touch. Gravitational waves let us feel the universe. For thousands of years, astronomy relied on light. First the stars we see, then radio, infrared, X-rays. Now we hear the cosmos vibrate. Each merger is a note. Together, they form a cosmic symphony. Hidden within its harmonies could be the whispers of quantum gravity, a rhythm slightly offbeat, a note that doesn't quite fit Einstein's scale. If such evidence is found, it would not diminish relativity but fulfill it. Einstein himself believed his theory incomplete. He spent his later years searching for a deeper unity between gravity and quantum physics. That dream now lives on in the data flowing from our detectors. The history of science is a chain of expansions. Newton's gravity gave way to Einstein's, and one day, Einstein's may yield to something richer. The pursuit may seem abstract, but its rewards rarely stay in theory. Quantum mechanics birthed the technologies that run our world: computers, lasers, GPS. Relativity corrects the clocks in those satellites, so your phone can tell you where you are. Quantum gravity. Should we one day master it, might bring unimaginable tools or insights, perhaps, into energy, computation, or even the fabric of reality itself. To picture how science adapts, think of the octopus, soft, boneless, endlessly inventive. It squeezes through impossibly small spaces and solves puzzles we didn't know it could understand. Physics must do the same, bend, twist, and adapt to find what lies beneath the surface. Whether space-time is woven from loops or strings, or from something we have yet to imagine, collisions of black holes and neutron stars may offer the first real clues. And so the listening continues. LIGO hums softly in the dark. Virgo and Cagra join the tune. Soon LISA will orbit the sun, stretching its triangle of sensors through space. Each waits for the next cosmic tremor, the next whisper from across billions of years. Maybe one day, in that faint vibration, we'll hear the edge of Einstein's melody, followed by a new refrain, one born from the quantum grain of the universe itself. When that note arrives, it won't be thunder or revelation, but something quieter, a pattern in the noise, a truth rising slowly from persistence and patience. From it, we may finally glimpse the bridge between the vast and the tiny, between space's smooth curve and quantum's restless shimmer. Until then, we keep listening, our instruments poised in silence, waiting for the universe to speak again. Not all opposites erase each other. Sometimes, when two forces meet, the outcome is not silence, but transformation. Matter and antimatter are the universe's most perfect opposites, mirror twins that, when joined, do not simply vanish, but flare into pure energy. Every breath of air, every grain of dust, every star above us is built from matter. Antimatter, though real, exists only in traces, its touch with ordinary matter ending in instant annihilation. And hidden in that violent balance lies one of the deepest riddles in science: why anything remains at all. The story began a century ago, when physics first looked inside the atom. Protons, neutrons, and electrons formed the foundation of matter. Positive, neutral, and negative charges keeping one another in check. Then came a surprise. In 1932, Paul Dirac's equations predicted the existence of a twin to the electron, identical in every way but with the opposite charge. When cosmic ray experiments soon revealed this particle, the positron antimatter, was no longer imagination but fact. Since then, we have found antiprotons, antineutrons, and even whole atoms of antihydrogen, tiny systems made of positrons orbiting antiprotons. They live only for moments, because the instant they touch matter, they self-destruct in a flash of light. When a particle meets its antiparticle, their masses are converted into energy, usually high-energy photons called gamma rays. This is Einstein's famous equation, E equals mc squared, acting at its most dramatic. A gram of matter meeting a gram of antimatter would release as much energy as a large nuclear explosion. The universe, however, keeps careful accounts. Nothing is lost, only changed. The charges cancel, the mass disappears, but the energy persists, transformed into radiation. On paper, matter and antimatter are mirror perfect, but the cosmos tells a different story. The Big Bang should have created equal amounts of both. If that symmetry had held, everything would have annihilated, leaving behind only light. Yet, against all odds, Matter won by the tiniest margin. One particle in a billion survived the universal fire. That slim surplus became all the galaxies, planets, and people. Physicists call this cosmic imbalance baryon asymmetry, and despite decades of searching, no one fully knows why it exists. Some clues come from the strange decays of subatomic particles like kaons and B-mesons. These particles sometimes favor matter over antimatter, breaking a delicate rule called CP symmetry, the combination of charge, C, and mirror image parity, A. The violation is minuscule, but it proves that the laws of physics have a slight bias. So far, that bias is too weak to explain our existence completely, yet it suggests that deep within nature's equations lies a preference, a tilt that tipped the balance toward matter. The search continues in laboratories like CERN in Geneva, where scientists make and trap atoms of antimatter using magnetic fields. These atoms must be handled like ghosts. Any contact with the physical world destroys them instantly. The achievement of holding anti-hydrogen for minutes at a time was a triumph of patience and precision. In 2023, researchers at CERN's Alpha G experiment even tested whether antimatter falls the same way as ordinary matter. The result, yes, it does confirm that gravity does not distinguish between the two. Antimatter is not repelled by Earth, nor does it rise. The universe treats mass and antimass alike in the pull of gravity. Despite its fragility, antimatter isn't confined to laboratories. Nature makes it too. Thunderstorms on Earth create bursts of gamma rays that briefly generate positrons. In space, pulsars rapidly spinning neutron stars, and the regions near black holes forge streams of antimatter as particles accelerate and collide at immense energies. When these antiparticles annihilate, they produce gamma rays that astronomers can detect with orbiting telescopes. Even within our own bodies, tiny sparks of annihilation occur every second. The radioactive isotope potassium-40, present in our tissues, occasionally emits positrons that collide with electrons, releasing minute flashes of light. Medical science harnesses this in PET scans, which trace those annihilations to create living maps of metabolism inside the human body. So, annihilation, though violent in image, is also a tool of understanding. It turns out that creation and destruction are inseparable at the smallest scales. When matter and antimatter meet, the result isn't erasure, but renewal, a conversion of substance into energy, of particles into light. Even the earliest seconds of the universe followed this rhythm: creation, collision, transformation. But why does the cancellation stop short? Why did matter endure while its twin disappeared? The prevailing idea is that the early universe contained just enough asymmetry for matter to edge ahead. Perhaps certain reactions favored particles over antiparticles by a hair's breadth, amplified by quantum fluctuations as the cosmos cooled. That trace difference, 1 in a billion, became everything we now see. The universe, in this sense, is the residue of an almost perfect cancellation. Antimatter also shows us how tightly nature guards symmetry. In the quantum world, pairs of matter and antimatter flicker in and out of existence continuously. Even empty space isn't truly empty. It teems with these short-lived partners, appearing and vanishing in fractions of a second. Their presence influences the behavior of atoms, the strength of forces, and even the expansion of the universe. The vacuum, it turns out, is not a void, but a restless field of balance and unbalance. The energy locked in annihilation is absolute. A gram of matter and a gram of antimatter together could power a city for days. It's no wonder science fiction imagines antimatter engines propelling starships. Yet in reality, producing and storing even a trace is an enormous challenge. At CERN, all the antimatter created in a year amounts to less than a billionth of a gram, at a cost far beyond any practical use. And if it escaped containment, the resulting explosion would vaporize the lab. For now, antimatter remains a scientific curiosity, a glimpse of perfect energy we can't yet touch safely. Still, the concept resonates beyond physics. Antimatter teaches that balance is not the same as sameness, and that opposites need not cancel completely. In nature, this principle appears again and again. Think of a zebra on the African plain. Black and white stripes that seem to oppose each other, yet together form a pattern of harmony and survival. The alternating bands don't vanish into gray. Instead, they create motion and confusion that protect the animal from predators and biting flies. The pattern's contrast is its strength. Matter and antimatter are like those stripes. Each is defined by the other. Each owes its meaning to opposition. Their collision doesn't result in emptiness, but in transformation, a flash of light that carries the story forward. Just as predator and prey sustain an ecosystem through tension, and night and day define each other by contrast, the universe itself seems to thrive on imbalance. Too much symmetry, and nothing happens. A little asymmetry, and existence blooms. Even gravity, the quiet architect of structure, plays its part. Matter and antimatter both curve space in the same way, pulling rather than pushing. Their annihilation releases light, and light too has weight in Einstein's sense. Energy bends space just as mass does. So even when matter and antimatter disappear, their echo remains in the geometry of the cosmos. The universe remembers every transformation. In the end, the meeting of matter and antimatter tells a simple but profound story. Total balance is sterile. Creation requires a flaw, a wrinkle, a refusal of perfect cancellation. The universe's very existence depends on that sliver of imperfection, a faint preference for matter that survived the fire. That leftover fraction became everything from galaxies to zebras, from gamma rays to human thought. When you look at the stars, you're seeing the aftermath of that imbalance, the light born from annihilation, and the matter that escaped it. The dance between matter and antimatter is not just destruction, but renewal, a cosmic heartbeat that pulses through atoms, storms, and living cells alike. Out of perfect opposition came imperfection, and out of imperfection, life. Let the night grow a little quieter, as if the sky has laid a soft blanket over your shoulders. Somewhere far away, far beyond the reach of light, two invisible giants are circling each other, tighter and faster, until they collide and become one. No fire, no smoke, no thunder. The explosion is hidden, silent, yet it ripples across the fabric of space-time, carrying its rhythm for billions of years. By the time those ripples reach Earth, they are only faint whispers. But in those whispers, the universe tells us a story. How heavy the black holes were, how fast they spun, how far away they lived. Those whispers first arrived in 2015. Two immense instruments, twin detectors called LIGO, heard them. Each stretched 4 kilometers long, one in Washington, the other in Louisiana. Lasers bounced between mirrors, so sensitive that they could measure a change smaller than a fraction of a proton's width. When the signal appeared, scientists saw two black holes, each 30 times the mass of the Sun, collide 1 billion light-years away. In less than half a second, they released more energy as gravitational waves than all the stars in the visible universe shine in that same moment. Einstein had predicted such waves in 1915, but doubted they would ever be detected. A century later, human patience proved him both right and wrong. Right that the waves existed, wrong that they would remain beyond reach. If you could see them, they wouldn't look like light or fire, but like ripples spreading across a still pond. Only the pond is space-time itself. A perfect circle in space would stretch and squeeze as the wave passed, shifting rhythmically as if the universe were breathing. Black hole mergers aren't the only drummers in this cosmic orchestra. Neutron stars, those crushed cores of exploded suns, also spiral together, releasing not just gravitational waves but light, gamma rays, and heavy elements like gold and platinum. Much of the gold on Earth was forged in such collisions billions of years ago, born in that brief moment when matter screamed through gravity's grip. In 2017, astronomers saw one of these events in both light and waves, a cosmic duet proving that the universe creates its treasures in fire and motion. Gravitational waves are often compared to the songs of great animals. Whales sing through the sea, their calls traveling hundreds of miles to reach other pods. Elephants murmur through the ground in infrasound, deep tones that humans can't hear but that carry for kilometers. Gravitational waves are like those calls, vibrations that move through space-time itself. They are too deep for our ears, but our instruments, LIGO, Virgo, Kagra, are built to listen. Before these discoveries, everything we knew of the cosmos came from light, visible, radio, X-ray, gamma. Each was a color in the grand painting of the sky. Gravitational waves added a new sense, hearing. They let us feel the universe. It's like standing outside during a storm after a lifetime of watching it through a window. You don't just see lightning anymore, you feel thunder beneath your feet. If we could speed up time and magnify these waves enough to see them, we might imagine standing at the shore of an invisible ocean. Waves roll in, not in water, but through reality itself. The ground stretches and contracts. The stars seem to quiver. Even time ticks a little faster, then slower, as though the universe is taking long, slow breaths. Each pattern carries the signature of its source: a black hole crash, a neutron star merger, a cosmic heartbeat. Think of a drum, strike it, and it sings in complex vibrations. From the tone alone, a skilled listener can tell how large it is, how hard it was struck, even what it's made of. The universe works the same way. Every gravitational wave is the sound of space-time's drum being struck by colossal events. Our detectors are the ears pressed to that drumhead, listening for faint, distant beats. The challenge is immense. The signals are buried in noise, from earthquakes, traffic, wind, even the vibration of air molecules. To detect them, scientists must isolate their instruments from every tremor, tuning them until light itself becomes the string of the universe's instrument. And yet, we're getting better. New observatories are coming. The Einstein Telescope in Europe, the Cosmic Explorer in the US, each more sensitive than before. And soon, far beyond Earth, 3 spacecraft will fly in formation around the Sun, linked by lasers across millions of kilometers. That mission, LISA, will listen to lower frequency waves, the songs of supermassive black holes. At the same time, Networks of radio telescopes are tracking pulsars, neutron stars that spin like perfect clocks. Their rhythms can reveal a background hum of gravitational waves that fills the cosmos like a deep, eternal drone. Each of these tools adds another instrument to our growing symphony. Together, they're tuning us to hear not just the recent beats of cosmic collisions, but perhaps the first pulse of the universe itself. The Big Bang, nearly 14 billion years ago, may have sent out gravitational waves as space expanded violently. Detecting those primordial ripples would be like hearing the first heartbeat of creation, a sound older than stars, older than light. Every source in this cosmic forest has its own voice. Black holes sing sharp, brief notes. Neutron stars hum in longer spirals. Some sing steadily, endlessly, sending out rhythmic ripples like crickets in the dark. For most of human history, we watched this forest in silence. Only now are we beginning to hear its songs. To imagine gravitational waves, picture two great fish leaping and colliding at the center of a lake. You never see the fish, only the ripples that reach the shore. From those circles spreading outward, you can tell that something powerful happened. Gravitational waves are just like that, ripples that reveal their source, even when the source itself is hidden behind darkness. Their faintness makes them all the more beautiful. They carry not just energy, but memory, the details of mass, spin, and orientation. Each wave is a messenger that traveled across time to find us. It is like hearing a wolf's distant howl in the wilderness and, from its tone, knowing its size, its distance, even its intent. These are the howls of the universe, encoded in space-time. When the first detection was made, humanity gained a new sense. Light had always been our guide. Now, sound joined it. It was as if the universe went from silent film to symphony, from a still picture to a living performance. Einstein's geometry had begun to sing. If you were to draw it, you might sketch two black circles, circling closer and closer, surrounded by ripples that race outward like rings in water. The squares and lines of space would twist and stretch, pulsing with each wave, shapes breathing as if alive. Birds create ripples in air as they fly, fish in water, and stars in space-time. If we could see these waves, the night sky would never seem still again. It would shimmer faintly, a living map of motion and memory. Nature offers countless metaphors. The song of a humpback whale carries across oceans. Gravitational waves carry across the universe. Whale songs tell of longing and distance, of recognition. Gravitational waves tell of collisions and creation. They both move through a medium unseen, their messages carried in rhythm and tone. To listen is to know that something vast and alive is speaking. These waves travel at light speed, never slowing, never aging. A merger that happened a billion years ago arrives today, in sync with its light. When both are caught, light and wave, the story becomes complete, a single event told in two voices, vision and vibration. Detecting them requires patience bordering on devotion. Most of the time, detectors hear only noise, the restless hum of Earth. But sometimes, a faint chirp rises from the static, a brief upward sweep of frequency, the universe clearing its throat to speak. It lasts less than a second, but it carries the weight of two suns. To hear such a sound is to feel the link between mathematics and emotion, between Einstein's equations and the tremor in your chest when you realize you're hearing the universe itself move. It is science, yes, but also poetry in its purest form. rhythm made of gravity, melody made of time. And while these discoveries may seem far from everyday life, history reminds us how ideas once abstract reshaped the world. Quantum mechanics gave us computers and lasers. Relativity corrects the clocks in your GPS so your phone can find the way home. Gravitational wave astronomy may one day yield technologies we cannot yet name, but even now, it gives us something rarer: perspective. Somewhere above, the stars look still, but they are trembling gently under invisible tides. Every mountain, every cloud, every heartbeat on Earth stretches and squeezes imperceptibly as waves of space-time wash through us. They pass without leaving a trace we can feel, yet they connect us to collisions billions of years gone. Each wave that arrives is a message, a song, a memory carried across cosmic time. Two black holes met long ago and left behind this music, still echoing. We are the audience, newly awakened to the sound. Listening to it, we understand that even the quiet universe is never truly silent. It hums, it breathes, and in that slow, steady rhythm, older than light itself, we rest.